All right, lesson 3 of our first unit is 1.3 geometric sequences. To start off, I want you to do this investigation. It's on your page, so you can see it in the picture here. We're going to take a piece of paper. So you can grab a piece of scrap paper from the cupboard. You can use some loose leaf out of your binder if you're at home. As long as it's like a pretty typical piece of paper, not like tissue paper or tracing paper, because then we're going to skew our results a little bit if that's the case. So it's a myth that you can't fold a piece of paper more than 7 times. We're going to test it, and while we're doing that, we're going to do a little bit of math. So I'm going to take my piece of paper. Right now it has 0 folds, so we're going to ignore the fact that we already have some pre-made creases. There is a single layer of paper. Fold it once, and you're going to record now the number of folds, which is 1, and the number of layers of paper, which is now 2. Now, it says we need to rotate the paper again. So I'm not going to fold it like this because that wouldn't be rotating it. Instead, I'm going to fold it in the opposite direction. Fold it like this. And now I have 2 folds, but 4 layers of paper. So you're going to continue doing this, and you're going to complete your table. I already know the answers, so I'm going to do that real quick, but pause it right now so that you can do it on your own. Okay, so once you've done your folds, could you fold it 7 times? I only got 6 on mine. So each time I folded, my number of folds increased by 1, but the number of layers changed differently. So what do you notice about the pattern? Well, it doubles every time. So the previous number of layers doubles once I've got my second layer, doubles to get my third fold. Once I've folded it twice, doubles again, doubles again, doubles again. So if we try and describe the pattern, we can call it a doubling pattern. You might also notice that those numbers of folds actually match up with an exponent. And so if we wrote 2 to the F, 2 to the F, then we could describe the number of layers based on that. So if 0 folds, 2 to the power of 0 is 1. 1 fold, that's 2 to the power of 1, or 2. So there's a couple different ways you can describe this pattern. This pattern is a geometric sequence. Again, sequences are strictly looking at numbers that follow a pattern. We're not doing anything to those numbers. It's just the pattern themselves. So a geometric sequence is formed by multiplying. Okay, so watch out, because now we're multiplying instead of adding and subtracting each term after the first term by a constant to determine the next term. Okay, and we're hearing this constant thing again. We're going to call it something different, so be careful. So for example, the sequence 3, 9, 27, 81 is a geometric sequence as each term is multiplied by 3, and the first term is also 3. That multiplier, that number that you're multiplying by every time, is called the common ratio. So be careful. Common difference is when we're talking about adding and subtracting. Common ratio is when we're talking about multiplying. So the common ratio is any non-zero real number and can be found by dividing any term by the preceding term. Okay, so what does that mean? Let's translate that into non-math English. Okay, so non-zero, so it means it can be literally any other number, fraction, decimal, anything. They're all allowed for R. So R can be any real number as long as it's not zero. Okay, how you're going to figure it out? Term 2 divided by term 1, term 3 divided by term 2. So the same sort of idea as when we were figuring out our arithmetic sequence. We always do the latter and how it's affected by the former, but this time we're dividing instead of subtracting. So we see for the sequence that we were working with, 3, 9, 27, 81, 9 divided by 3 is 3. Nope, and there's a typo there. Sorry, that's not 4. That should be R. 27 divided by 9 is also 3, which is R. And 81 divided by 27 is also 3, which is R. R being your common ratio. So for each of the following, let's figure out our common ratio. So we've got potentially 16 divided by 4, which would be 4. But we can double check that this is in fact a geometric sequence. We can go 64 divided by 16, which is also 4. This means that our common ratio is 4. For B, exact same principle applies, except we're dealing with decimals, so it's a little bit less pretty, maybe a little bit harder to do mental math with. 1.5 divided by 0.5 is 3. 4.5, sorry guys, 4.5 divided by 1.5 is also 3. And finally, 13.5 divided by 4.5 is also 3 because they are all the same. It is a geometric sequence and our R value is 3. Our last one, this one becomes a little bit trickier. So you're going to want to have your calculator around for this. You're going to go 1.6 divided by 2. Now, you might be able to piece it together. Okay, that's 16 over 20, which means it's 8/10 or 0.8. If you can't spot that, it's okay. Don't worry about it. Use your calculator. We can double check this by going 1.28 divided by 160, or not 160, 1.6. For this one, I definitely won't need my calculator. 1.28 divided by 1.6, and I get 0.8 again. And if I check the third one, I should get that as well. And so my common ratio is 8. And I can feel pretty confident with that. Other examples include an infinite geometric sequence, which could be going on forever, but there is also a potentially finite geometric sequence if we just stop multiplying. So you got to be careful. This dot, dot, dot that we were so adamant on before, it's important. So if we have a dot, 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 it means it is going to be infinite. If it ends with no dot, 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 then we call it finite. It stops after a fixed number of terms. So I'm just going to highlight that because That might be a word that we don't usually hear. There's also variations. We can be multiplying by a large number, like a number bigger than 1, in which case we're going to be doubling or tripling, anything along that lines. And so it is increasing in value if it's positive, but it's also divergent. Okay, not the book, but the math term. And what that means is it does not approach a constant value. It's going to keep spreading out. Sorry. It's going to keep spreading out. It's going to keep getting bigger and bigger and bigger. Alternately, you can have convergent sequences. Those are ones that get smaller and smaller. They're getting smaller and smaller, but specifically they are getting one specific number. So this example here of a half, a fourth, an eighth, a 16th, a 32nd, and so on is convergent because it is getting close to a constant value of 0. Now, convergent series do not always have to approach 0, but they have to approach something. Okay. Finally, we can look at this last one, 1, -2, 4, -8, 16, and it is neither increasing or decreasing. It's fluctuating on both sides, which is a red flag that probably my R value is not positive. But either way, it is also divergent because the numbers still keep getting larger in magnitude. Magnitude just means size. It completely ignores whether it's positive or negative. Okay, so that particular pattern is an unusual one. So you might want to put a star beside it and consider that. So we said R must be non-zero. Why? Why does R need to be non-zero? Well, consider what we're doing with R. We are multiplying, and if we multiply by 0, our answer will be 0, which means that every term in our entire sequence would be the same value. That's obviously not the case for all the examples we just looked at, so R cannot be 0. It has to be another number. So let's look at some examples of applying this idea. So part A, determine the 10th term of this geometric sequence. We've got 2, -6, 18, -54. So again, we're going to need to decide how exactly we're going to do this. We could, hypothetically, keep multiplying, but there is actually a better way. Okay, so we're going to use an equation instead. It is on your formula sheet, but I don't have it in this booklet here, so we're going to write it out. So it looks similar, at least to start, to our arithmetic sequence, but it changes quite quickly. So we've got term 1, which is still the same. Now we've got multiplying by R, okay, and that fits with our definition. And that exponent piece that we mentioned way back at the beginning of this lesson comes into play here. So this is our equation. If you want to write it down, that's probably a good idea. I know it's on your formula sheet, but it's always nice to have in your notes as well. So we need to figure out our R value, and then we're going to need to figure out our 10th term. So how do we figure out R again? Well, we divide a later term by its previous term. So I'm just going to do -6 divided by 2 to figure out r, which is negative 3. Again, if you want to check that, 18 divided by negative 6 is also negative 3, so we're good to go. Now we can start plugging into our formula. So Tn, or the nth term, is not what we're looking for. We are looking for the 10th term. Term 1 is the value 2. R is negative 3. Put it in brackets because we're not subtracting, we're multiplying here. And n is 10, and we're subtracting 1 in the exponent. This means that we can rewrite it as 2 and negative 3 to the power of 9. Again, those brackets are super important. If you want to plug this into your calculator, because I don't know the 9th power of 3, maybe you do. If you've got a knack for memorizing facts, we're going to go 3 to the power of 9. We know it's going to be negative because it's an odd exponent, and it's going to be 19,683. We're going to double that, so times 2, and our final answer, so term number 10 is going to be negative 39,366. So you can see in just those short few terms, going from term 1, which had a value of 2, to term 10, we are now up at almost 40,000. So geometric sequences are very, very different than arithmetic sequences. Part B asks, identify the sequence as increasing or decreasing, and convergent or divergent. Because we're flip-flopping between negative and positive, it is neither increasing nor decreasing. But it is divergent still. Because it still is getting bigger and bigger and bigger. Example 2. Create a geometric sequence whose 6th term is 27. So for this one, you could create any sequence you wanted to, but you need to remember that you're working backwards. So we're needing to figure out all of these terms. Term 4, term 5, term 6. Is the only one we're given, 27. So you can do this a couple ways. I'm not sure why I did that. My personal preference would be to choose an R value. And then we can just go from there. So R can be 3, because it's a number that goes into 27 nicely. 27 divided by 3, because we're working down back towards term 1, is going to be 9. 9 divided by 3 is 3. 3 divided by 3 is 1. 1 divided by 3 is a third. 1/3 divided by 3 is actually 1/9. And there we go. There's our general equation. We could have used that and chosen our first term and then solved for r and gone from there. But That way was a little bit easier. It was nice and clean because we got to choose our R value. But that is not always the case. Sometimes we need to find R. So again, we're going to start with our equation as usual. Tn equals T1 R to the power of n minus 1. We're told it's a finite geometric sequence, and we are told that we need to determine term 2 and term 6. So, in order to be able to figure out term 2 and term 6 and build from 1 and 5, first we need that R value, that common ratio. So we are going to plug and chug. We've got 567 equals 7 multiplied by R to the power of 5 minus 1. Now again, it's 5 because 567 is term 5. From here, we've got some moving around to do. So I'm going to divide that 7 away. So I'm trying to isolate my R. So it's R to the power of 4. Again, I'm going to need my calculator. So it's 567 divided by 7, 81. And I'm going to need to take the 4th root of that in order to eliminate my exponent. So the 4th root of 81 is 3, and so R is 3. Great, now I can solve for term 2 and term 6. So term 2 is going to be term 1, or 7, because again, I'm using this equation for everything. So term 1 is 7. R now has a value of 3, and n is going to be 2 minus 1. So it's just going to be 7 multiplied by 3 to the power of 1, if we think about it that way. And so term 2 is going to be 21. Term 6, on the other hand, is going to be a little bit bigger. We're going to start with term 1 again. So still 7 multiplied by 3, but this time we're going to be multiplying by 3 to the power of 6 minus 1, or 3 to the power of 5. Sorry about that. So we've got 3 to the power of 5. If we plug that in, 3 to the power of 5, that gives us 243 multiplied by 7, and now we're looking at 1701. And so there are our two answers for example 3. That's how we can work backwards. It's a little bit more tricky, perhaps, than arithmetic sequences, and then use that R value to go forward. Now, part B of this question is even more tricky. The last term is 45,927. How many terms are in this sequence? All right, so here we go. How on earth are we going to figure this out? Well, we start with our equation. Tn equals, and we go term 1 multiplied by R to the power of n minus 1. Well, 45,927 equals, and term 1 was 7 multiplied by 3 to the power of some number minus 1. From here, we can keep going. Divide by 7 on both sides. So we're trying to isolate that n now. 45, 9, 27 divided by 7 is 6,561. And that's 3 to the power of n minus 1. Now, you'll have to remember some of your exponent laws to try and simplify this a little bit further. Or you can just start with guess and check right from here. I'm going to show you using exponent laws. So we're going to rewrite this as 6,561 equals 3. And subtracting in exponents is like dividing. So it's actually the same as 3 to the n divided by 3 to the power of 1. So I'm dividing by 3 once. Well, now that 3 can go away at least by multiplying. So 3 to the power of some number is going to be equal to 3 times 6,561, which is 19,683. From here, unfortunately, based on the math that you know right now, you'd have to work backwards and just keep dividing 19,683 by 3 until you get to 1, and that means you'd have to count all of those values. Now that does not sound like a lot of fun to me, but there is a shortcut that we'll be learning in grade 12, so we won't go there this year. This year we would have to stop here for now and guess and check. So take a second, grab your calculator, pause the video, and start typing in 19,683 divided by 3. Now depending on how your calculator works, you can keep hitting the equal sign and just keep track. How many times do you press that equal sign until the value that shows up on your screen is 1? That is going to be your n value. I've already done this, and so I know that n is equal to 9. Now you can double check by typing in 3 to the power of 9 in your calculator, and it will give you 19,683. What does this n actually tell me? Well, it tells me that there are 9 terms in this sequence. So, last example. Statistics Canada estimates the population growth of Canadian cities, provinces, and territories. The population of Nunavut is expected to grow annually by 0.8%. In 2009, its population was about 30,000. Estimate the population in each year to the nearest 1,000. Okay, so before we move on, before we even start dealing with which years we're looking at, the first thing we need to do is pick out some numbers. We've got 30,000. That is term 1. That is where we're starting. Okay, so we've got term 1, and our R value is going to be that 0.8%. But this is where it gets a little tricky. We are expecting growth. If we just use that percentage as it is, if we just take 0.8% and we don't add it back to that 30,000, we are going to run into big problems because it will shrink the number by a lot. So instead, when we write R, there's 2 things we need to remember. We need to include our original population, which means we need a value of 1. Percent is also out of 100, so it's not 0.8 that we're going to be writing, it's 0.008. So that is a big one. Lots of people forget the 1. If you do that, you're going to get a super tiny number for the population, like negative exponent in scientific notation, just like Tiny, tiny number. So be super careful on that one. We also need to figure out which term 2013 actually is. Well, since 2009 actually counts as term 1, it's the value of 1, we actually are going to add that difference, so 2009 to 2013, that's 4 years. We're adding that on to term 1. So this is going to be not term 4, but term 5. From here, we fill in our equation. Term n equals term 1 multiplied by r to the power of n minus 1. So that, in this case, it's going to be term 5 equals 30,000 multiplied by 1.008 to the power of 5 minus 1. Now, I'm just going to plug this all into my calculator because it can be entered all as one long chain. So 30,000 multiplied by 1.008 to the power of 4. My final answer is going to be 30,971.58. But notice the question asks to the nearest thousand. And so when I round this off here, I'm just going to cut it off to 31,000 people. Okay, moving forward, we're going a little bit later. So 2049 is 40 years after 2009. That means it's not term 40 though, it's term 41. So watch out. Again, we're using the same equation though, otherwise, so Tn equals T1 R n minus 1. So term 41 is equal to 30,000 multiplied by 1.008 to the power of 41 minus 1, or 40, which is what I was about to write. Again, you can just plug this into your calculator. If you've got a fancy enough calculator, you can actually just go back to the previous line and edit it, so it'll save you lots of keystrokes. And I get as my answer 41,261, which we're going to round off to 41,000 people. Carried away there. All right, so last example. Sometimes you use a photocopier to make enlargements or reductions. Suppose the actual length of a photo is 25 centimeters, and the smallest size that a copier can make is 67% of the original. What is the shortest possible length of a photograph after 5 reductions? Express your answer to the nearest tenth of a centimeter. So again, let's take up our highlighter, pick out some information. 25 centimeters is going to be our term 1. 67% is going to be our R value. But again, we want to put it in decimal form, so it's going to be 0.67. This time I do not include that 1 in front of the decimal place because I'm not making it larger. I don't want to include the original size plus some. I'm taking away that other piece. I'm only going to be left with 67%. Now, if we're doing 5 reductions, And we've got term 1 is with 0 reductions. 5 reductions is actually going to take us to term 6. From here, we use our equation. Term n equals term 1, our common ratio to the power of n minus 1. So we're going to have term 6 equals 25 multiplied by 0.67 to the power of 6 minus 1, or to the power of 5. From here, we plug into our calculator, 25 times 0.67 to the power of 5. And that gives me 3.375. But we're asked for the nearest tenth, so we cut it off here. Tenth of a centimeter. And so my actual answer is going to be 3.4 centimeters. So significantly smaller if you keep photocopying. And that is the end of this lesson. So grab your workbook and get practicing.